Welcome to our exploration of why language models hallucinate. This paper dives into why artificial intelligence systems sometimes make up false information, much like a student guessing on a tough test question. Have you ever wondered why even the most advanced artificial intelligence models can confidently state things that are completely wrong? This phenomenon, known as hallucination, happens because during training and evaluation, models are rewarded for guessing rather than admitting when they're unsure. It's not some mysterious flaw. It stems from basic statistical errors in how these models classify information. If a model can't tell the difference between facts and falsehoods, it's naturally pushed to make things up. What's more, the way we test these models encourages this behavior, as guessing can boost scores on common benchmarks. To fix this, we need to change how evaluations are scored, steering the field toward more trustworthy systems. Artificial intelligence language models often produce confident but false statements, which hurts their reliability. This issue, called hallucination, isn't the same as human imagination and remains a big problem in the latest models. For instance, consider this question. What is Adam Tauman Kalai's birthday? If, just respond with the day and month. In a real-world test, a top open-source model gave 3 wrong dates, like 0307, 1506, and 0101, even though it was only supposed to answer if it knew the correct one, which is in autumn. This shows how models can invent details, as seen in more complex examples in the paper's tables. Hallucinations are a specific type of error in language models, and we can study them using learning theory. We look at errors as a subset of all possible plausible outputs, with the rest being valid, and analyze the statistics behind why these mistakes happen. This table reveals a telling pattern. When asked about Adam Kalai's dissertation title, 3 popular language models, ChatGPT, DeepSeek, and Llama, all produced incorrect answers, failing to get both the title and year right. This isn't just a random mistake. It's a concrete example of how these models can confidently generate false information, even on straightforward factual queries. Now, let's connect this to the core issue. We're applying our theoretical framework to understand why these plausible falsehoods, known as hallucinations, occur. Our approach includes the concept of a prompt, the question or instruction given to the language model, which sets the stage for how errors might emerge in the response. You might think that if we trained language models on perfect, error-free data, they'd never make mistakes. But here's the surprising insight. Even with flawless training data, the very objectives we use to train these models would still lead them to generate errors. Why? Because the training process rewards statistical patterns that can include inaccuracies. In real-world scenarios where training data is messy and full of half-truths, the error rates are likely even higher. Our analysis provides lower bounds on these errors, drawing from established principles in computational learning theory to show that some level of error is unavoidable. Our error analysis isn't limited to specific models or methods. It applies broadly to various types of language models, including those used for reasoning or retrieval, and doesn't depend on details like next word prediction or transformer architectures. We focus on the 2 main stages of training, pre-training and post-training. For hallucinations, researchers often categorize them into intrinsic types, which contradict the user's prompt, and extrinsic types, which clash with training data or real-world facts, helping us pinpoint where things go wrong. In a simple test asking how many D's are in, DEEPSEEK, models like DeepSeek v3 gave inconsistent answers, sometimes 2, other times 3. while others like Meta Artificial Intelligence and Claude 3.7 Sonnet produced even wilder guesses like 6 or 7. This variability highlights how hallucinations aren't just about intrinsic errors, but also extrinsic ones, where the model's output contradicts basic facts from the training data or reality, showing that our theory explains a wide range of error types. During pre-training, the base model learns language patterns from a massive text corpus. But here's the catch. Even if that data were completely error-free, the statistical objectives we optimize would still cause the model to make errors. This might seem counterintuitive, as some models could avoid errors by always saying, "I don't know," or by perfectly memorizing the corpus. Our analysis digs into why certain errors are inevitable after pre-training, revealing the inherent limitations in how these models learn. To understand this, we draw an analogy to binary classification. Imagine asking, is this a valid language model output? Generating a response is trickier than just answering yes or no because it requires evaluating every possible candidate. Formally, we define the "is it valid" problem, where a training set labels responses as valid or errors, helping us model how pre-training leads to mistakes by forcing the model to make probabilistic choices rather than certain ones. Let's start with some examples to illustrate valid and invalid text. On the left, we have correct phrases like, "Greetings, how can I help?" which represent proper language use. In contrast, the right side shows errors such as "Greetings, how can I help?" with misspellings, highlighting common mistakes that models might make. Moving to counting tasks, the text states there are 2 Ds in ladder, and there is 1 N in piano, demonstrating simple factual checks that models should handle accurately. Similarly, there are 3 Ls in spell is correct, but there is 1 G in cat is wrong, since cat has no G, showing how models can err even on straightforward queries. For arbitrary facts, we see Mia Holdner's birthday is 4/1, and I don't know Zidane's birthday, where the first is a specific claim and the second admits uncertainty, emphasizing the challenge of invented details. Examples like Colin Merivale's birthday is 8/29 and Yago Pere's birthday is 8/21 continue this, illustrating how models might generate plausible but unverified information. Figure 1 depicts the "is it valid" task, where models learn to identify valid text from labeled examples. It shows classifiers that work well for clear concepts like spelling but fail due to poor modeling, or when data lacks patterns, such as with arbitrary facts, underscoring why errors persist. In this supervised learning setup, the training and test data are balanced mixtures. Half are valid examples from pre-training data, and half are random errors. This framework allows any language model to act as an "is it valid" classifier, linking generative errors like hallucinations directly to misclassification rates. The key mathematical insight is that the generative error rate is at least twice the "is it valid" misclassification rate, meaning that even small classification mistakes can lead to significant errors in text generation, highlighting the statistical nature of these issues. While language models are good at avoiding obvious errors like spelling mistakes, not all mistakes are hallucinations. The connection to "is it valid" misclassification reveals that generative errors stem from statistical factors in pre-training, similar to those in binary classification. Decades of research, as visualized in Domingos, 2012, show cases like accurate classification on separable data, poor modeling leading to errors, and situations with no discernible patterns. Section B.3 analyzes factors like epistemic uncertainty, where lack of data patterns causes unavoidable errors. This approach unifies earlier work, such as Kalai and Vempalla's 2024 study on arbitrary facts with no learnable patterns, like the birthday examples. The is it valid reduction not only covers this, but improves their bound. If 20% of birthday facts appear only once in pre-training data, models are expected to hallucinate on at least 20% of such facts. Our analysis extends this to include prompts and, responses, which are crucial for understanding hallucinations fully. Post-training aims to reduce hallucinations by refining base models, but why do overconfident errors persist instead of models omitting information or saying, We explore a socio-technical explanation for this and discuss ways the field can better suppress these stubborn hallucinations.
We are Genipad. Your likes and subscriptions inspire us to create more videos and keep improving our service. Want to turn your own content into videos? Visit us at www.genipad.com.
Have you ever noticed how people sometimes make up answers when they're unsure? For instance, students might guess on multiple choice tests or bluff with plausible-sounding responses in written exams, even if they lack confidence. Similarly, language models face evaluations that mimic these human tests using binary scoring systems where a correct answer earns 1 point and blanks or, responses get 0. This setup encourages guessing, leading to overconfident and specific answers, like stating September 30th instead of a vague sometime in autumn for a date question. Many benchmarks for language models, such as accuracy or pass rate metrics, mirror standardized exams, and optimizing for these can inadvertently promote hallucinations. Humans learn to express uncertainty in real-life situations, but language models are constantly in test-taking mode due to evaluations that penalize uncertainty, creating a misalignment that fosters errors. It's not a new idea that binary grading fails to capture hallucinations, but previous efforts have focused on finding a perfect way to measure them, which isn't enough. The real issue is that most evaluations penalize uncertainty, making it hard for models to admit when they don't know. Imagine two models. Model A is aligned, always signaling uncertainty and avoiding hallucinations, while Model B never shows uncertainty and always guesses when unsure. Under common 0 to 1 scoring, Model B would score higher, creating an epidemic where abstaining is punished. This means that just having a few hallucination evaluations won't solve the problem. Instead, we need to adjust the many primary evaluations to stop penalizing uncertainty and abstentions, fostering a more honest approach. Our contributions pinpoint the key statistical reasons why hallucinations happen, from their start in pre-training to their persistence after post-training. We make a novel link between supervised and unsupervised learning, showing that even if training data includes, examples, errors can still arise. Hallucinations stick around because most evaluations reward guessing, similar to how students might bluff on tests. To address this, we propose statistically sound changes to existing evaluations that could lead to better ways of reducing these errors. To our knowledge, the connection we draw between supervised learning, like binary classification, and unsupervised learning, such as density estimation, is a fresh perspective. This method of reducing one learning problem to another is a well-established technique in the field, used to show that certain problems are equally challenging, as seen in prior research like Bagel-Zimmer et al. 2016. Many studies have delved into why language models hallucinate, citing factors like model overconfidence, randomness in decoding, snowballing effects where small errors lead to bigger ones, long-tailed training samples that don't cover all cases, misleading alignment training, spurious correlations, exposure bias, the reversal curse, and context hijacking. Similar error sources have been explored in broader machine learning and statistics, highlighting that this isn't just a language model issue, but a common challenge in artificial intelligence. The most relevant theoretical work comes from Kalai and Vempala, 2024, which we build upon in our analysis. Let's explore how this research builds on earlier studies about hallucinations. Previous work connected good Turing estimates to hallucinations, inspiring Theorem B, but it missed key elements like uncertainty expressions, supervised learning links, and prompts. Another study by Haneke et al. Used an interactive approach with a validity oracle to train models that reduce hallucinations efficiently with data, but it's not practical for computation. Recent theories by Calavasis and others highlight a fundamental trade-off. Models must choose between avoiding invalid outputs and generating diverse content, meaning any generalizing model will either hallucinate or collapse in creativity. What techniques help reduce hallucinations after training? Methods like reinforcement learning from human feedback, artificial intelligence feedback, and direct preference optimization have shown success in cutting down on errors like conspiracy theories. However, fine-tuning on new information can backfire, initially lowering hallucinations only for them to rise later. Interestingly, both the language used in queries and the model's internal signals can predict accuracy and uncertainty, and inconsistencies in answers to similar questions offer another way to detect and fix hallucinations. Many other strategies exist to fight hallucinations, as detailed in surveys by G and Tian, and new benchmarks have emerged to evaluate them. Yet these tools haven't gained much traction in the artificial intelligence community, with reports noting adoption barriers. Beyond simple yes or no certainty, researchers propose nuanced language to express degrees of uncertainty, and the field of pragmatics, which studies how context shapes meaning, is becoming crucial for improving how language models communicate information clearly. Pre-training creates a base language model that tries to mimic the probability distribution of text from its training data, a process called density estimation in unsupervised learning. This involves modeling probabilities over text or other inputs, aiming to capture the underlying patterns. Why is it hard to prove base models make errors? Some models, like one that always says, or just repeats training examples, avoid errors if we assume the data is perfect. But these fail at the core goal of density estimation, which is to accurately model language statistics. The ideal model matching the training distribution would avoid errors, but achieving this is challenging and key to statistical language modeling. Even with massive amounts of training data, we can't eliminate all errors in language models. Our analysis reveals that well-trained base models are still prone to making certain types of mistakes, which is an inherent part of their design. Why is it harder for a model to generate correct text than to simply judge if text is valid? This insight allows us to apply computational learning theory, which treats errors as normal and predictable, to understand why generative models like language models fail. A language model is essentially a probability distribution over all possible texts, and when prompts are added, the core idea remains the same. For instance, without prompts, models might generate general statements like birthday facts, while with prompts, they could be asked for a specific person's birthday, as shown in the figure. Is a language model just an advanced autocomplete tool? Our analysis goes beyond that, applying to any model that estimates probability distributions, not just those predicting the next word. It's easy to blame hallucinations on bad starting phrases, like, Adam Kalai was born on, where the model struggles to find a valid ending. But statistically, the word-by-word generation is no different from how humans speak step by step. Errors actually stem from the model's attempt to mimic the true language distribution, though the specific model design can add extra mistakes. In a base model without prompts, it acts as a probability distribution over a set of possible text strings, where each string is considered plausible, such as a full document. This set is divided into errors and valid examples, with errors and valid texts being separate and non-overlapping groups. The error rate of the model measures how often it produces mistakes. The error rate is defined as the probability that a randomly generated text from the model falls into the error set. In simpler terms, it's the chance the model outputs something incorrect, calculated by sampling from its distribution. Training data is assumed to come from a perfect distribution where no errors exist, meaning the probability of errors in training is 0. If the training data had noise or partially correct statements, we'd expect even higher error rates than what our analysis predicts. Now, let's formalize the is-it-valid binary classification problem. It involves learning a target function that determines if a text is valid based on a distribution that mixes samples from the model's output and uniformly random errors in equal parts. The distribution for the is-it-valid problem assigns probabilities. If a text is valid, it uses half the model's probability for that text, and if it's an error, it uses a uniform probability over all errors. The target function labels valid texts positively and errors negatively. Our analysis connects the model's error rate to the misclassification rate in the is-it-valid problem, showing a lower bound that helps quantify unavoidable errors. The misclassification rate in is-it-valid is defined as the probability that the learned function disagrees with the true labels. If the model's probability for a text is high, it uses that in the calculation. If low, it defaults to a threshold, highlighting how classification errors relate to generation errors. In this setup, the base model acts as an is-it-valid classifier by setting a probability threshold at 1 divided by the size of the set B. This means the model decides if a text is valid based on whether its probability exceeds this cutoff. Although computing these probabilities is often efficient for base models, it's not essential for the theoretical lower bounds we're discussing. Corollary 1 states that for any training distribution where all data is valid and any base model, a specific relationship holds. The formula shows that the error in the base model is at least half the error in the is-it-valid classification. Here, error represents the base model's error rate, and error_IIV is the misclassification rate for validity. This highlights that generative errors are inherently tied to classification mistakes. In this equation, delta is defined as the absolute difference between the probability assigned by the base model and the true probability for the set A, where A includes all texts with probability greater than 1 divided by the size of B. This delta measures how well the model's probabilities align with reality, and the errors are derived from earlier equations 11 and 12. This relationship applies to all base models, meaning they will inevitably make errors on inherently unlearnable facts, like guessing birthdays not in the training data. In such cases, the is-it-valid error is high, while delta and the ratio of valid to invalid texts are small. For example, with birthdays, there are 364 incorrect options for every correct one, plus the possibility of saying, I don't know. This corollary is a specific instance of a more general theorem that includes prompts, and later theorems handle cases with small sets, like true or false questions. The constant 2 in the bound is quite tight. For large invalid sets and small delta, the is-it-valid error can approach 1/2, while the base model error nears 1, implying that the is-it-valid error is always at least 1/2 in these scenarios. To connect this error analysis to hallucinations, think of the invalid set as containing plausible generations that include falsehoods. Another common definition of hallucinations is text not grounded in training data or prompts. Fortunately, the lower bound still applies here because we assume the training data is entirely valid, so any factual error in the output cannot be traced back to correct training data, reinforcing that such errors are unavoidable. Now let's explore calibration and why delta is typically small after pre-training. Calibration refers to how well a model's predicted probabilities match actual outcomes. Without any language knowledge, one could achieve delta equals 0 by using a uniform distribution, but this doesn't mean the model is accurate. An auditor can estimate the invalid set by comparing samples from the training distribution and synthetic generations. Drawing an analogy to weather forecasting, a minimal calibration check is if the average prediction matches the average outcome, like rain frequency. A stricter requirement from Dowd 1982 is that for every probability threshold, the actual frequency should match the prediction on days with that forecast. Here is a straightforward reason why delta is usually small with the standard pre-training cross-entropy objective. The loss function L of P is the expected value of negative log probability over the true distribution. Minimizing this cross-entropy loss during pre-training encourages the model's probabilities to closely match the true data distribution, which keeps delta small and ensures better calibration. Imagine rescaling the probabilities of positively labeled examples by a factor s greater than 0 and then normalizing them. The formula defines a new probability distribution, P underscore S. If the original probability is above the threshold 1 divided by the size of B, it's scaled. Otherwise, it remains unchanged. This adjustment helps analyze how probability shifts affect model behavior and errors. Let's look at this calibration curve that shows how well a model's confidence matches its actual accuracy. On the left, we have a pre-trained model with perfect calibration. When it says it's 80% confident, it's right 80% of the time. The expected calibration error is 0, meaning no mismatch between confidence and performance. On the right, after reinforcement learning training, the calibration gets worse, with an ECE of 0.074. Notice how the points drift away from that perfect diagonal line, showing the model becomes overconfident or underconfident in its predictions. This figure shows GPT-4's calibration before and after reinforcement learning training, using multiple choice questions with simple A, B, C, D answers. The left plot reveals the pre-trained model is well calibrated. Its confidence levels accurately reflect how often it gets answers right. After training, the calibration shifts, demonstrating how reinforcement learning can disrupt this careful balance between confidence and accuracy. Here's an interesting mathematical insight. We can measure how sensitive the model's loss function is to scaling adjustments. The Greek letter delta represents the magnitude of change in loss when we tweak the scaling factor away from its normal value. This formula calculates that sensitivity measure, delta. It's essentially the absolute value of how quickly the loss changes as we adjust the scaling factor s, evaluated at the point where s equals 1. Think of it as measuring how stable the model's performance is against small adjustments to its probability scaling. If this sensitivity measure delta equals 0, it means we could improve the model's performance simply by rescaling its probabilities. Since language models are powerful enough to handle such scaling adjustments, optimization during training should keep delta small. This sensitivity measure focuses on a single threshold point, making it less comprehensive than metrics like expected calibration error that consider all confidence levels together. Here's a crucial clarification. Hallucinations are only inevitable for base language models, not all artificial intelligence systems. Some argue hallucinations can't be avoided, but we could easily create a non-hallucinating system using a simple question-answer database and calculator that only responds to predefined queries and otherwise says, "I don't know." The mathematical proof shows that error-free language models must be poorly calibrated with large delta values. In reality, calibration emerges naturally from standard training objectives, and empirical studies confirm base models tend to be well calibrated, unlike post-trained models that may sacrifice calibration for other goals through reinforcement learning. Now we're expanding our analysis to include prompts or contexts. Each example consists of both a prompt drawn from a distribution and a plausible response. This generalizes our earlier framework that focused only on responses, allowing us to study how different prompts affect model behavior and hallucination patterns. Let's dive into how prompts affect model responses. For any given prompt, we can think of valid responses as those that are correct and erroneous ones as mistakes. The training process shapes the model's conditional probability of generating a response given a prompt, essentially defining how likely it is to produce valid versus erroneous outputs. This setup helps us analyze error rates by extending to joint distributions, where the probability of errors depends on both the prompt and response probabilities. Training examples typically come from valid dialogues, similar to methods like distillation in other studies. While it's unrealistic to assume training data perfectly matches real prompt distributions, deviations can lead to even higher error rates. In the "is it valid" problem with prompts, the goal is to classify responses correctly, but the distribution now includes prompts and random erroneous responses. The classifier uses a threshold based on the model's probability output, and earlier results generalize to show that errors are fundamentally tied to this classification process. This theorem establishes a key bound on errors in base models. It states that the error rate in generating responses is at least half the error rate in the "is it valid" classification task, scaled by factors related to the number of valid and erroneous responses per prompt. The variable delta measures the difference between the training and model probabilities, indicating how well the model aligns with the training data. Delta is defined as the absolute difference between the probability assigned by the training distribution and the model for cases where the model's probability exceeds a threshold based on the minimum number of erroneous responses. This helps quantify deviations that contribute to errors. By adjusting probabilities through rescaling and normalization per prompt, we can keep delta small, meaning the model remains stable and close to the training distribution. This is optimized during training by minimizing the cross-entropy loss, which measures how well the model's predictions match the actual data. What drives hallucinations in artificial intelligence? Decades of research on binary classification errors shed light on this. Statistical complexity plays a role, such as in cases like arbitrary birthdays where patterns are hard to learn. Model-specific issues, like errors in simple tasks such as letter counting, also contribute. Additionally, factors like garbage in, garbage out, seen in conspiracy theories and poor prior assumptions, can exacerbate these errors, highlighting the multifaceted nature of generative mistakes. Why do models invent facts out of thin air? This often happens due to epistemic uncertainty, where the necessary knowledge is missing from the training data. The Vapnik-Chervonenkis dimension, a concept from learning theory, measures how many examples are needed to learn a function family. High VC dimension means learning requires many samples, making it tough for models to grasp patterns. In cases of random arbitrary facts where correct answers are unpredictable, this leads to high uncertainty and errors. Arbitrary facts are defined with a fixed prompt distribution and an, option. For each prompt, a single correct answer is randomly chosen from a set, and the model has a probability of answering or saying, I don't know. Erroneous responses are all other options in the set, while valid ones include only the correct answer and I don't know. This setup models scenarios where facts lack patterns, making errors more likely. The analysis assumes each fact has only one correct way to express it, as in the birthday example where the format was specified. However, in reality, multiple valid expressions might exist, potentially increasing error rates as models struggle to choose the right one. Did you know that language models make more mistakes when facts can be stated in many different ways? For example, with birthdays, famous ones like Einstein's are mentioned a lot in training data, so models rarely get them wrong. But obscure birthdays might only appear once, like in an obituary, leading to errors because the model hasn't seen enough examples to learn them properly. The paper sets a lower limit for hallucinations based on how many prompts in the training data appear only once, ignoring cases where the model says it doesn't know. This means that even with perfect training, some errors are unavoidable because of these rare prompts. A singleton is defined as a prompt that shows up exactly one time in the training data, without any abstentions. The singleton rate is just the fraction of these unique prompts in the dataset, which helps measure how much the model might struggle with unfamiliar inputs. Ever heard of Alan Turing's missing mass estimator from the 1950s? It's a clever idea where you use the proportion of samples that appear only once to estimate the probability of unseen events. In AI, singletons act as a stand-in for all the new things a model might encounter, showing why hallucinations can't be fully eliminated. The theorem for arbitrary facts states that any algorithm trained on a set of samples will have a certain error rate, with high probability no matter how it's designed. This formula shows that the error rate is at least half the singleton rate, adjusted by other factors. It highlights that hallucinations have a fundamental lower bound, meaning you can't reduce mistakes below this point no matter what you do. Moreover, there's an efficient method that outputs well-calibrated probabilities, ensuring the model's confidence matches reality with high reliability. This formula gives an upper bound on the error rate, relating it to the singleton rate and other terms. It shows that errors can be controlled but not eliminated, emphasizing the inherent limits in AI performance. Earlier versions of this work didn't include prompts and abstentions, but follow-up research has studied hallucinations empirically, linking them to singleton rates and calibration in real-world scenarios. Why do models misclassify things even when they're trying their best? It could be because the model type is too simple to capture complex patterns, like using a straight line to separate circular data, or because the model isn't trained well enough despite having the potential. Agnostic learning deals with this by defining the minimum error possible for any classifier in a given family. This formula represents the optimal error rate for a classifier family, showing the best possible performance even if the model isn't perfect. It's a way to measure how good the model can get, highlighting that some errors are unavoidable due to limitations in the model's design. Did you know that if a classifier is too weak, it's bound to make a lot of mistakes? In language models, when we set up classifiers based on probability thresholds, they can only do so much. This formula defines a classifier that checks if the model's probability for a response is above or below a threshold, helping us spot errors by setting confidence levels. From a key theorem, we get a direct link between generation errors and how well these classifiers can perform. This inequality shows that generation errors are at least twice the best possible misclassification rate, meaning models can't avoid making some mistakes no matter how we tweak them. In simple multiple-choice setups with only one right answer, we can tighten the bounds and remove calibration issues, making it easier to see the error limits, even with just two choices. For pure multiple-choice scenarios, where each question has exactly one correct answer, Theorem 3 gives us a clear error bound. This formula tells us that the error rate is at least twice 1 minus the optimal classifier error, highlighting that models will always struggle to be perfect in these cases. Let's look back at old trigram models from the 80s and 90s that predicted words based on just the previous two words. They often produced gibberish because they couldn't handle longer contexts. Here are examples with prompts about someone losing it, where the correct responses depend on gender pronouns, showing how models might mix them up. Each context has only one valid response, but trigram models can't always pick the right one, leading to errors. Corollary 2 states that for uniform prompts, any trigram model must have at least a 50% error rate, which is huge. This happens because with two choices and trigram limitations, the best classifier error is 50%, forcing generation errors to be high. Bigger models need way more data to improve. Now, think about the letter counting example from earlier. It's a model weakness issue, as some advanced models handle it well with reasoning. For instance, a reasoning model carefully spells out words step by step to count letters accurately, showing how better approaches reduce mistakes. This suggests that reinforcement learning models are superior for tasks like reasoning because they process prompts as tokens rather than characters, overcoming representation hurdles. All right, let's dive into some extra reasons why AI models mess up and spit out false information. It's not just one thing. Multiple factors team up to cause these errors. Think of it like a perfect storm of issues that we've already talked about, plus a few new ones I'll explain. First up, computational hardness. Ever wonder if even a super smart AI could solve any problem? Well, no. There are fundamental limits from computer science that say some tasks are just too tough for any classical computer. For example, if you ask an AI to decrypt a code it can't crack, it might guess wrong instead of saying, "I don't know." This ties back to earlier theorems showing that errors are unavoidable in these tricky scenarios. Next, distribution shift. Imagine training a model on one set of data, but then testing it on something totally different. Like teaching it with cat photos and then asking about dogs. That mismatch causes big errors. In language models, if a prompt is rare or weird in the training data, like a trick question about feathers and lead, the model might fumble and give a wrong answer. Even though reasoning models can handle this better, poor model design often plays a bigger role in these slip-ups. Now, let's talk about GIGO, garbage in, garbage out. If the training data is full of mistakes, I will copy those errors. It's like learning from a textbook with typos. You end up repeating them. This isn't just a guess. Studies show models replicate factual errors from their training sources. The stats for this are pretty straightforward, so the paper skips the deep math, but it's a key reason why base models can be unreliable. Here's the good news. Post-training can clean up some of this mess, like fixing common myths or conspiracy theories the AI picked up. But hold on. The next part explains why this isn't a perfect fix. In fact, post-training might even make some hallucinations worse, which we'll explore in detail. So, what's the deal with post-training? It's supposed to turn a basic autocomplete model into one that doesn't confidently lie, except maybe in creative writing. But reducing hallucinations is a huge challenge, because current benchmarks and leaderboards actually encourage them. This isn't just a tech problem, it's social too. We need to change how we evaluate models and get everyone on board with better standards to stop rewarding fake facts. Let's break down how evaluations make hallucinations worse. Most tests use a simple right or wrong scoring system that gives 0 points for answers that show uncertainty, skip sketchy details, or ask for more info. Metrics like accuracy and pass rates dominate the field, but they push models to guess instead of admit they don't know. This binary approach hides the nuances of real-world knowledge. Did you know that in many AI evaluations, saying, "I don't know," is actually the worst thing a model can do? That's right, current grading systems heavily penalize uncertainty and instead reward overconfident guesses. This setup aims to balance two things: how accurate the model is when it does answer, and how often it provides a response. But here's the kicker. Prioritizing accuracy over completeness can actually reduce hallucinations by discouraging the model from making things up when it's unsure. Let's break this down with a simple analogy. Imagine you're in a quiz where you have to answer questions, and you can either guess or say, "I don't know." The grading is binary, only right or wrong, and "I don't know" always scores 0. Even if you have some belief about the correct answer, the best strategy isn't to abstain. It's to take your best shot. This shows that in AI, when models are trained with such rubrics, they're pushed to guess rather than admit uncertainty, which fuels hallucinations. Here's a key observation. For any prompt, no matter what the model believes about the correct answer, the optimal response is never to abstain. This means models are essentially forced to guess, even when they're not sure. This formula represents the idea that abstaining responses are excluded from the set of best guesses. In simple terms, it shows mathematically that models should avoid saying, "I don't know," and instead pick the response they think is most likely correct, reinforcing the push towards overconfidence. So what does this mean for real-world AI evaluations? Most popular tests use this binary grading, which punishes honesty about uncertainty. Even if we create perfect methods to reduce hallucinations, they might not work because the main evaluations still reward guessing. It's like trying to fix a leaky faucet while the whole plumbing system is designed to overflow. We need to rethink how we test AI to encourage more truthful responses. Think about human exams. They often reward bluffing too. In many standardized tests, like the SAT or GRE in the past, wrong answers were penalized, so test takers had to guess only when they were confident enough. This mirrors the AI problem, where models need clear thresholds to decide when to answer. The key is that in humans, real-life consequences, like embarrassment, curb fabrication, but AI lacks that social feedback. To tackle this, the paper suggests adding explicit confidence targets to AI evaluations. For example, instructions could tell the model to only answer if it's highly confident, with penalties for mistakes. This way, models learn to weigh their certainty, just like humans do in exams with partial credit systems. Here's a concrete example of how to phrase this in a prompt. Answer only if you're confident, because mistakes cost you points, correct answers earn points, and saying, I don't know, gets 0. This sets clear rules for when to guess, helping models avoid unnecessary hallucinations. Different confidence thresholds can be used, like 50%, 75%, or 90% certainty, each with its own penalty for wrong answers. A threshold of 0 means always guess, which is what happens in binary grading. By adjusting these values, we can fine-tune how models express uncertainty, making them more honest in their responses. Ever wondered how AI benchmarks handle it when a model says, I don't know? This table breaks down popular evaluations. And guess what? Most use strict binary grading, meaning they only give points for right or wrong answers, with no credit for abstaining. That's like a test where guessing is better than admitting uncertainty, pushing models to hallucinate instead of being honest. It's a big reason why AI fakes facts, and we need to rethink how we score these systems. Let's dive into this table of benchmarks. It's a real eye-opener. Each row shows a different test, like GPQA or MMLU Pro, and they all use multiple choice or exact match scoring with binary grading. That means if the model isn't sure, it gets 0 points for saying IDK, forcing it to take a risky guess. Wildbench is a bit better with partial credit, but overall, this setup rewards overconfidence. Why does this matter? Because it teaches AI to bluff rather than be cautious, leading to more made-up answers in real-world use. Here's a key insight. If a model's confidence in its answer is above a certain threshold, it's actually better to guess than to say, I don't know, and score 0. This creates a mathematical push for models to hallucinate when they're unsure, because staying silent doesn't pay off. It's like a game where bluffing is the winning strategy, even if it means spreading false information. So, how do we fix this overconfidence problem? The paper suggests making confidence thresholds explicit in the instructions. Tell the model exactly when to answer based on how sure it is, like setting a 75% confidence bar. Previous methods often left this vague, leading to inconsistent results. By being clear, we can grade models objectively and reduce arguments about fairness. It's a simple change that could make AI more honest, as one model could excel across all thresholds if it knows the rules up front. Another cool idea is to add these confidence targets into mainstream evaluations like SWE Bench, which tests software patches. Instead of creating separate tests for hallucinations, embedding thresholds in widely used benchmarks makes uncertainty less penalized. This amplifies efforts to cut down on fake facts without forcing a trade-off between accuracy and errors. It's about integrating honesty into the systems we already rely on. With explicit confidence targets, there's one optimal behavior for all scenarios. The model should only answer when its probability of being correct is above the threshold, and otherwise say IDK. This unified approach eliminates guesswork and encourages models to be transparent about their uncertainties, making them more reliable in practice. Ever wondered how we can make artificial intelligence more honest about what it knows? The paper introduces behavioral calibration, where instead of forcing models to output probabilities, they must only respond when they're super confident, say at least 75% sure. This way, we can check accuracy and error rates across different confidence levels, avoiding the mess of endless ways to phrase correct answers. It's a practical fix that could make evaluations fairer and reduce those annoying fake facts. Why is it so hard to tackle AI hallucinations? They're complex beasts, and any statistical framework has to simplify things, leaving out some details. Let's dive into what this paper covers and what it might be missing. Did you know that hallucinations are all about plausible falsehoods, not just random nonsense? The paper focuses on these believable errors, assuming models rarely spit out gibberish. Even if we add nonsense into the mix, the core theorem still holds, showing that errors are tied to how we define what's valid or not. What about open-ended prompts, like writing a biography? Hallucinations can creep in here too, with errors defined as any false statement in the response. But it's not all or nothing. We could measure the degree of hallucination based on how many mistakes are made, making it more nuanced. Think adding search or reasoning fixes everything? Not so fast. While tools like retrieval augmented generation help cut down on hallucinations, the paper shows that the binary grading system still pushes models to guess when search fails. Plus, for intrinsic errors like miscalculations and counting tasks, search doesn't always save the day, highlighting the limits of these enhancements. Ever had a misunderstanding because of hidden context? Like if someone asks about phones, meaning landlines, but the AI talks about cell phones. The paper's error definition doesn't account for this external context, suggesting it'd be cool to include hidden factors for judging mistakes, tying into the idea of aleatoric uncertainty where some errors are just unavoidable. Is it just right, wrong, or I don't know? The paper points out that this trichotomy oversimplifies things, ignoring different error levels or uncertainties. But adding an IDK option is a step up from a simple right-wrong split, and using explicit confidence targets in evaluations could make AI more practical and honest, even if it's not perfect. Did you know language models can signal uncertainty in more ways than just saying, "I don't know"? They might hedge their bets, leave out details, or even ask questions to clarify things. But here's the catch. While it's useful for models to give confidence estimates, sometimes it sounds totally unnatural, like saying, "I'm 1/365th certain about a birthday." That just doesn't flow like human talk. So this paper zooms in on the big statistical decisions behind what gets said, skipping the complex social rules of language. All right, let's wrap this up with the key takeaways. This paper breaks down why language models hallucinate, starting from their initial training all the way through later tweaks. In pre-training, errors pop up just like in supervised learning. It's not some mystery, but a natural result of minimizing cross-entropy loss. Think of it as the model learning to make educated guesses, which can lead to confident mistakes. Here's a game changer. Many language model flaws can be caught with just one simple test. For example, if a model overuses words like certainly, a single evaluation can flag that without messing up other checks. But the real issue? Most mainstream evaluations actually encourage hallucination by rewarding overconfident answers. By tweaking these tests to reward uncertainty instead of punishing it, we can cut down on fake facts and open the door for smarter, more nuanced models in the future.